Greetings, internet users. We constantly use energy in our daily lives. Energy is present in our devices and our bodies, allowing us to move and perform work. It doesn't take up space, although we can feel its effects and measure it. This mysterious force is always present and brings about changes in matter. Thanks to energy, our world changes, and so do we. In the 4th century before our time, Aristotle defined energy as the capacity to transform and produce changes in objects. We can only measure energy through the effects it produces on matter. Nowadays, we know many types of energy. Electromagnetic energy propagates through waves in space and is the radiation from our sun that reaches us in the form of light and heat. Chemical energy is stored in matter and atomic bonds, and we use it in wood and transportation, among other things. Thermal energy is one of the most commonly used forms of energy thanks to atomic reactions such as boiling water, heaters, and even the human body itself. The sun is just one example. Electrical energy comes from the flow of electrons and electric fields and is used in all kinds of devices and transportation. Kinetic energy is the energy of movement, like the flow of a river, a moving ball, or a planet, and so on. Nuclear energy is found in the atomic nucleus and can be released through fusion and fission. Gravitational energy provides an attractive force between two bodies with mass. Therefore, we know that the energy around us follows two fundamental laws. The first law tells us that the energy of the universe is constant and does not disappear, it only transforms. This means that since the beginning of the universe, the amount of energy has not changed, it has always remained the same. Some of it has transformed into matter, which is just another form of energy but much more concentrated and structured, having mass and occupying space. According to Einstein's equation, energy and matter are interchangeable. In reality, everything is energy in one way or another. We are mostly energy because there is 99% empty space between atoms. The rest consists of quantum fields, such as matter and energy, which are interchangeable. So, one could say that we are 100% energy, constantly renewing and maintaining locally stable systems for brief periods of time with low entropy, like our bodies. This is true because between 7 and 10 years, all the atoms and cells in our bodies have been renewed. We are not the same person, we are a copy of what we were, and that copy continues making more copies and transforming along the way. Aging would be like making a photocopy of another photocopy continuously. The second law tells us that energy can transfer from one body to another in the form of heat, waves, or work, but it tends to degrade. For example, when we eat, we are nourishing ourselves with the energy contained in food to perform our biological functions. However, a large portion of that energy dissipates as heat. In fact, we only harness 5% of the ingested energy. This also happens with all our devices and objects in the universe. There is no system or technology that can fully harness energy according to the second law of thermodynamics. We will always lose energy during transfer. The more we advance in technology, the better we can utilize energy, but never completely, as it is an unbreakable law of the universe, leading to entropy. What happens to the unused energy? It returns to the universe to be recycled. Energy is never destroyed. The universe continuously provides us with free, however, we must use it responsibly, without tricks or changes in the tariff. What we do with it is up to us. This energy is measurable thanks to the property of bodies that accumulate it, and its effects are observable everywhere. The exact explanation of what energy is lies in its nature as a characteristic of spacetime itself, transforming the contained bodies in a given moment of time. Spacetime is a human abstraction or a real entity according to relativity. It is a structure of 3 spatial dimensions plus time, sustaining the entire universe we know, and it is continuous without fragmentation. This is the most solid theory currently. However, when we delve into quantum mechanics, fragmented spacetime appears. Recent studies indicate that spacetime arises from quantum entanglement, which is the association of 2 or more subatomic particles behaving as a single entity, regardless of the distance between them. According to this hypothesis, spacetime is merely a graph that contains all the maximum information within a certain volume, limited by a total area. In quantum mechanics, this is known as the Bekenstein bound, an upper limit to the entropy or information contained in a finite region of space. This also includes energy. The universe would be a 3-dimensional structure where all the information is stored on a 2-dimensional surface where time does not exist. But where does all this energy we enjoy come from? It has always existed. The creation of stars and planets always involves a type of energy that we know is contained within spacetime. To discover the origin of the energy in our space, we must go back to the origins. Brace yourself, as it might blow your mind. We determined that the energy we currently have has always existed in the vacuum, but has undergone many transformations. Zero-point energy is an experiment that shows us that no matter what we do in a vacuum, there will always be energy. Let's define what the vacuum is. The vacuum is a space with the lowest possible amount of energy and completely devoid of matter. Even in the vacuum, there are quantum fields resulting from the activity of virtual virtual particles. The false vacuum or Higgs vacuum we currently exist in gives mass to particles and, consequently, the existence of the four fundamental forces that bind matter. However, this vacuum is also filled with quantum fluctuations. Within these fluctuations, pairs of virtual particles and antiparticles of positive and negative energy appear, annihilating each other and returning the energy to the vacuum that created them. These particles are called virtual because they are so short-lived that their properties cannot be measured. It is a way for us to imagine the quantum vacuum, as all particles can acquire the property of being wave-particle duality. To understand this, we must think in terms of wave phenomena. The best way to understand the state of the quantum vacuum is to imagine the surface of a moving lake where waves of all frequencies overlap. That's how the quantum vacuum is, with continuous waves generated by virtual particles. This means that the quantum vacuum is not constant. It does not have a fixed energy, and at any moment an event can occur. Although we may not see these virtual particles, we know of their interaction with others. As Albert Einstein said, not everything that exists can be proven, nor does everything that can be proven exist. There are many types of vacuum, depending on the level of energy in these fluctuations. Currently, we live in a universe that is a limited and self-contained quantum field, which is quite stable but not in its most stable state. The Higgs vacuum can be compared to the electrical power supply in our homes that keeps our devices running, expressed in watts. If there is a power outage, nothing can function. In the case of the Higgs vacuum, the power that sustains everything is 246 gigaelectronvolts. If an extraordinary event or an unpredictable quantum fluctuation occurs to a lower energy state, the vacuum can decay. It would be similar to a blackout but with more dramatic consequences because the energy that makes up our space-time transforms, and the bodies within it disintegrate, returning all their energy to the vacuum. To compensate for the loss of energy, inflation occurs. You should think of all bodies as a type of energy transformed in space-time, dependent on the Higgs field, just as a virtual character depends on a computer to function. In this case, the Higgs field would be electricity, space-time would be the computer, and for us, the virtual characters, along with planets and galaxies. Observations suggest that our universe emerged from a false vacuum. In the theory of quantum field, the false vacuum is quite stable, but if it materializes at some point with enough energy, it disintegrates and forms a bubble due to gravitational rebound, creating a new universe. The theory of cosmic inflation tells us that everything that existed was occupied by a field called the inflaton, which was in a false vacuum full of quantum fluctuations that caused it to reach a true vacuum with lower energy. However, due to repulsive gravity and fluctuations, it expanded because the field sought to reach a state of lower energy from a state of higher energy. The only possibility was to release all the initial energy during the expansion. Also, pairs of particles and antiparticles were still being created, but the initial expansion of the early moments was so rapid that it prevented their mutual annihilation. This is when they appeared as real particles. One of them, the Higgs boson, spread throughout the universe. The existence of this new field raised the energy of that state above the previous state. This field was called the Higgs field, and the particles that interacted with it gained potential energy. Through the famous equation E equals mc squared, they acquired mass. Therefore, the origin of energy lies in the quantum vacuum, in the virtual particles that mysteriously appear and annihilate, acting as intermediaries for other real particles with longer lifespans. For a brief period, a pair of virtual particles can travel between real particles, interacting with them before disappearing and returning the borrowed energy to the vacuum. For example, when a photon interacts with its virtual particles that arise from the quantum vacuum, a virtual pair of an electron and positron is produced. The pair of antiparticles is absorbed at another point, where another photon emerges from the energy they borrowed from the electron-positron pair. These phenomena are unpredictable according to Heisenberg's uncertainty principle and occur in the vacuum, regardless of its type. The vacuum does not reveal its deepest mysteries. It is illogical, but it provides us with energy. No one knows where these virtual particles come from, but what we do know is that they can violate the principle of conservation of energy for a very short period. They appear out of nothing and then disappear, continuously and intermittently. Sometimes, the pairs cannot annihilate each other and escape, transforming into real particles through extraordinary events, such as escaping the horizon of a black hole or the inflaton field itself. Cosmologist Alexander Vilenkin believes that beyond the observable universe, there are infinite other universes, nested within each other following a fractal pattern, like a set of Russian nesting dolls floating in a false vacuum, indefinitely repeating until reaching the true vacuum from which the first Big Bangs emerged. Whatever the origin of energy may be, it seems to be eternal and continuously emerging from the vacuum. It is the power plant of the cosmic machinery to which we have no access. It is evidence that a higher being provides us with energy without charging us a penny, or perhaps the vacuum itself is a natural entity that gives existence to everything we see. If the universe is infinite, created by an infinite God, what remains remains of it all? God or the universe? We have learned that nothing is permanent. Don't seek eternity because nothing lasts forever, not even the vacuum. Everything must be transformed over and over again to continue existing, and every particle, every atom of matter, has a function. The universe created you to offer the world something different from what others offer. In the end, the creative and destructive energy of worlds is the only real and infinite thing. If you liked this video, give it a like and don't forget to subscribe. Activate the bell icon to receive all notifications. Share it on social media and leave your comment.